So we'll start today with the last part of chapter 11. After this there's one last chapter that's about partial differential equations and how to numerically solve them. Coupled, not coupled. Today we'll finish again chapter 11, and I try to have about 15 minutes left at the end so that we can talk about the final project, okay? That is the, I'll give you some hints, okay? So, as you know, I always start with clearing the screen and clearing everything. So clear and then CLC, clear screen. And chapter 11 is on numerical integration. So we have some function. We don't have the antiderivative of that function, but we still like to calculate the area between a certain lower bound and upper bound. In this chapter also referred to as A and B. So we have the Newton code rules, which are the trapezoidal rule and Simpson's rule. And Simpson's rule, you have different variants. Then we talked about their composite implementation. So traditional rule is that you integrate in one single step from the lower bound to the upper bound. A composite rule, a composite trapezoidal or Simpson's rule is that you don't integrate in one step from the lower to the upper bound, but instead divide the interval in panels of equal size, equal width, and solve the integral for each individual panel. And then you take the sum of the integral of those individual panels. Then you have the total integral between A and B. So we've seen that Gaussian Quadrature is the preferred method. So with the trapezoidal rule and Simpson's rule, you define the x values at which you like to compute the function values. And then you do the integration. But your selection of the x values might mathematically not be optimal. And what means optimal is that you select the values of x and f in such a way that the resulting error of the integral is as low as possible. Now, Gaussian Quadrature is a method that helps you select which x values to take. And the resulting integral is essentially the sum of the weights of each x value times the function value at that given x value. And there are scripts that will give you the optimal x values for a given number of nodes, a given number of x values you like to use. And we've seen that if we use two x values, then one x value is minus 1 over the square root of 3, and the other x value is 1 over the square root of 3, and both carry a weight of 1. So you compute the function value at both x values, minus 1 over the square root of 3, you compute the function value at 1 over the square root of 3, and that you multiply with the weight of 1. So essentially you take the sum of the two function values, and then there's a constant in front that you need to calculate. And that's then the estimate of the integral. If you have more nodes, more x values, then there's this built-in function, or at least the author wrote it, which is GL table or GL node WT, that gives you, for an even number of nodes, an even number of x values, the optimal x values and the corresponding weights, W. So the input to this function is how many x values do you like to use to integrate that function, and the output is the optimal location of the x values, x and W. But this Gaussian Quadrature assumes that your integral is between minus 1 and 1. So the x values will be located between minus 1 and 1. Your integral might be between minus 10 and 10, or 0 and 10, or 3 and 7. So then you need to linearly transform the x values that come out of this function to the domain that you're interested in. And we looked at that before. There is this function here, I guess it's this one here, that says xi is the optimum value coming out of the GL node WT script, so that's the optimum location according to Gaussian quadrature. B is the upper part of your integral, A is the lower bound, now etc. So this is how you scale the values that are optimal in the domain between -1 and 1 to C, and that C is your integral that you're trying to resolve, or at least the position in that integral. Okay? Now, so Gaussian quadrature is quite optimal, okay? So with a relatively small number of x values, you can solve numerically the integral of a function. This requires that the function is available, okay? Because you need to evaluate the function at those optimal x values that come out of that script, that GL node WT. In cases that you don't have a function, but you only have x versus y values, you need to resort to like a trapezoidal rule, where you do a composite implementation, because there's no other choice. So keep that in mind, okay? So most of these integration rules assume that you have the function script. In some cases you don't have that, so that methods like Gaussian quadrature or adaptive quadrature are useless. You need to just use the trapezoidal rule with intervals or panels that can actually vary in width, because you can have an x value at 0 and the next one at 1, and then you can have the next x value at 3. So the first panel has width 1, the second panel has width 2. So keep that in mind. So you need to use a composite trapezoidal integration rule. Now, we've seen that the Gaussian quadrature rule is best if we do have the function script, okay? But there is ways actually to improve the Simpson and the trapezoidal rule. We can make them adaptive, and that's also called adaptive quadrature, like Gaussian quadrature, in which the x values are predetermined by a script on the interval between -1 and 1. Adaptive quadrature is somewhat similar, but instead of predefining the x values, what it does, it just starts out with an interval, and each time it makes the interval smaller, 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 and smaller. So the panel width gets smaller, 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 and smaller, until you hit the point that if you make the interval smaller again, that there's no improvement in the accuracy of the integral. So the author wrote this script, which is called adaptive Simpson, and that's an adaptive implementation of the Simpson rule. Okay, and I will leave that for now. Essentially what that does, that applies Simpson's rule, first on the entire interval, then on half of that interval, then a quarter of that interval, and then it hits a point where the distance, the panel width, if you make it smaller, that the estimate of the integral does not get any better. So that's where the script stops. And we can actually, you can go in that function, I already did this, and now we can actually integrate a certain function. Let's see if we do this function over here. We've seen this function, yeah, that's x times exponent minus x. And let's also derive fx here. So let's do this again, so that we can compute the analytical integral, so that we have a comparison. So this is our original function. And now execute this adaptive Simpson script. Okay? And so now I get an estimate of the integral between, this is the function name, that's an inline function. Yeah, you see that there, fun is inline x times exponent minus x, and again the dot is used after the x so that we work with vectors. 0 is a, lower bound of integral, 4 is the upper bound. This is the accuracy I have, so this is the distance to the true analytical integral. 10 is the maximum number of iterations I like to do, and 1 is the iteration starter. Okay, the level where you start. You can start at a higher level if you wish. So instead of starting at 0 and 4, you could immediately say, you know, I start at level 2, which is 0, 2, and 2 and 4. So you divide it in half. So our estimate is 0.9084. So that should be the integral of this function between 0 and 4. So the area of this curve between 0 and 4, so the area under the curve between 0 and 4 is equal to 0.9084. Okay, so now let's see if this makes sense. We can do this analytically because we have that toolbox, at least it's on my computer, and you see that it's almost a perfect result because the difference is the error is minus 3.2 times 10 to the power minus 11. So the difference between what we estimate numerically with the adaptive Simpson and what the analytical result is really, really small. And why is that so small? Because I use 1e minus 10. I could have said, you know, use 1e minus 5. I'm satisfied, iterate till the difference is 1e minus 5 or smaller. So we can execute this and then we can calculate the error again. You see that the error is larger now because we have a different tolerance criteria here now. So the smaller you make this value, the smaller the error will become. So now obviously, and that's what I show here as well, it's the same story where I use 5e minus 6, and you see that I actually halt because the maximum iteration that I use is minus 1. So I don't really iterate. And why it is minus 1 is because the author has said that the maximum level is the value that I enter here in my function plus 2. So if I enter minus 1, then the maximum level of iteration is 1 because I add 2 to it. That's in the function. And why that is, that's just a choice of the author. That's not so important. Point is that I only do 1 iteration and the code starts complaining here that the iteration has been halted because what you see that the error does not satisfy 5e minus 6. The error is larger. So the code wants to continue. But we actually said, based on the settings we provided there with minus 1 and 1, is we do not want you to continue. So the error that comes out is larger than what we satisfy simply because I should have used a larger value here, not minus 1. I should have used like 5. Then the maximum level is 7. Okay? So there's all kind of text here. Now the author also writes a demo of this Simpson, and this is an example where you see how this methodology works. Is on top you have a nonlinear function called the humps function that's built in MATLAB, and here you see on this axis, this is the x value, yeah, both between 0 and 2 in this case, and here you see the different x values that are used to calculate the integral numerically. So what do you see? Very clearly that when the function is highly dynamic, here the distance between two x values is really small. Once the function becomes more linear, like in this domain, you see that the distance between two x values becomes larger. And that makes sense because it's much easier to integrate a linear function than it is to integrate a nonlinear function. Because if my function is linear, then essentially I only need 2 points, yeah? If I have an entirely linear function like this, I only need this point, and I can apply the trapezoidal rule. Yeah? And calculate the area. This function is highly nonlinear, so in parts, the more nonlinear, the more x values this adaptive quadrature is suggesting. And why? To minimize the error with the actual analytical result. So you still need quite a number of x values, as you see here, to successfully solve this function. And what you see here is the author uses the option flop. That was an old function script in MATLAB, an old built-in function that calculated something related to computation time. And that is no longer available. I have an old version. I work with MATLAB 2007. You guys probably work with MATLAB 2011 or 2012. I don't know. So you might get a warning or something similar to this. Okay? Point is, adaptive quadrature just selects the values of x so that the resulting integral has a minimum error. But it's different from Gaussian quadrature in that Gaussian quadrature always has the same x values irrespective of the function that you're actually integrating. It always comes up with the same location of the x values between -1 and 1 irrespective of the function that you're trying to numerically integrate. Adaptive quadrature, these results will depend on the actual function that you have. So please, so what you saw here is the result if I use a tolerance of 5e minus 5. Okay? So if I say, for me it's acceptable that the error between the true integral and the numerical estimate that we estimate with the adaptive Simpson, it's acceptable if that is smaller than 5e minus 5. And someone else will say, oh, that's way too large. Or someone else will say, oh, that's more than good enough. Here you can see, if I change that to a larger value, keep this in mind, yeah? What you see is this. Because now what I used a tolerance of 0.1. So as soon as I increase the tolerance, the number of x values that are being used reduces heavily. Because I'm okay with a larger error. Okay? Again, so Gaussian quadrature always will give you the same location of the x values irrespective of the function you're trying to integrate. So it gives the location of the x values between -1 and 1 and the corresponding weight. And the integral is then some constant, a minus or b minus a divided by 2 times the sum of the weight times the function value at each x value. That's the integral. So the x values are always the same. So if you have an integral that ranges between -1 and 1, you're done essentially. If you are between -10 or 10 or 10 and 100, you need to scale first those x values to the domain of interest using the scaling rule. That is Gaussian quadrature, so always the same location of the x value. Adaptive quadrature is different in that sense, like the Simpson's rule, in that the location of the x values depends on the function dynamics. And you see more x values being used at places where the function shows more dynamics. And that is to minimize the error in the numerical integral. Okay? Now, what we've discussed so far is a lot of it is built in MATLAB. So there are built-in functions. Okay? And that's useful. For instance, trapezoidal integration, the function trap-c is a built-in function that you have that will do trapezoidal numerical integration for you. And you supply the x values and the corresponding function values to it. And what it will return is a numerical estimate of the integral. Quad is another built-in function, and that's adaptive Simpson quadrature, what we just talked about. Quad 8 used to be a built-in function, but that's no longer existing. So if you want to use quad 8, use quad L, and that's not adaptive Simpson, but that's adaptive Lobato quadrature. So we haven't discussed that, that's just a slightly different rule. But what's important, that you know these two functions. This one does trapezoidal numerical integration, the second one does adaptive Simpson quadrature. Okay, so now let's use these functions. So let's specify again that our function is x times exponent minus x. That's our built-in function. Let's calculate the function value f at a given number of x values. So what I say here, okay, this is my inline function, and now I want to evaluate this function between 0 and 4 with step size 0.1. So now I should have, these are my x values and these are my corresponding function values. Yeah? Now, I can just very simply integrate, if I do this, I underscore t, which means the trapezoidal integral is trap-c, that's that built-in function, asks from you the x values and the corresponding function values. And it gives you an estimate, 0.9075. Okay? So we don't have to write our own script, it's already built in. This is not a composite variant. You can write your own composite variant if you just execute this script on each interval of x, if that's what you want to do. Now, numerically, you know, we see that we integrate between x is 0 and x is 4. X is 0 is the minimum and x is 4 is the maximum with a step size of 0.1. Now we can also compute what the analytical result is. That's based on our antiderivative by filling out the upper bound and the lower bound, and you see that we are pretty close. We get 0.9075 and the analytical result is 0.9084, but that's because we use the step size of 0.1. If I use a step size of 1, we can redo this and now calculate the integral. We are pretty far off. So again, the result with the trapezoidal integration rule is fine if you use enough x values. Okay? So obviously, I can also make it really nice if I actually have a step size of 0.01, because if I now do the integration, you see, I'm going to get the same result as the analytical result there, I underscore an on top. But I use the step size of 0.01, which means I have to use 4001 or so, what is it, 401? 401 x values to get a similar result. It's not particularly efficient, but anyway. Now, let's look at, so this is the built-in trapezoidal integration rule. Okay? Now, let's look at this quad function. Quad corresponds to quadrature. And this is Simpson's, adaptive Simpson's quadrature, okay? So let's specify that we like to integrate the same function between 0 and 4, because we already had the lower bound was 0, the upper bound was 4. But with quad we need to specify explicitly what a and b are, With the Trapezoidal function, we only specify the x values and the corresponding function values as two inputs. And the function does the rest. The quad function asks you to specify the lower bound and the upper bound. Because it does not ask you which x values to use. Because the function will determine which x values to use. Yeah? That's the adaptive quadrature. So we only specify the function, which is an inline function. Yeah? So our function is x times exponent minus x. And then as second input argument we have lower bound, upper bound. So this is very easy to use. You don't have to specify the x values. With the trapezoidal rule, you need to specify the x values you are using at the corresponding function values. So this adaptive Simpson's quadrature selects the location of x. So what you see, we're getting here 9084, which is almost perfect because the analytical result is 9084. So we can also use that Lobato quadrature method and we're getting the same result. But whether you use quad or quad L, you see that the function call is the same. And you're typically going to get a very similar answer. So you should know how to work with these built-in functions, okay? So you specify a function as an inline function, okay? And then you just specify, I like to integrate this function between the lower bound a and the upper bound b. And that gives you an estimate numerically of the integral. And in this case, we know what the true answer is, because we know that this was the antiderivative of x times exponent minus x. So we can directly calculate what the integral is analytically between 0 and 4. So that's how we got to this number. And you see that we're going to get really good result. Now, you can also specify, if you like to exercise these functions, you can also specify another input argument, and that's the accuracy of the resulting estimate. So if we look at line 210, now you see quad, function a and b, and then there's a fourth input argument which says that's 1e minus 6. And that more or less gives you the accuracy, the tolerance. So we can execute this again, and now we can check, and indeed what you see is that my resulting estimate, or our resulting estimate of the numerical integral of our function x times exponent minus x, the error is smaller than 1e minus 6, because that was our tolerance. It needs to be smaller or equal to 1e minus 6. Okay? So you can specify another input argument if you wish, and make that small. Now let's consider another function. This is a famous function called the humps function, okay? Believe it or not, it's built in MATLAB, and the function script is called humps, which input variables x. So x are just the x values at which you like to evaluate this function. And now we like to integrate this function with the built-in functions, okay? Now, we can integrate this. Let's integrate this between 0 and 2. Now, we know how to do that. That's very simple. That's quad. This is the function name. And because it's built in MATLAB, we don't have to specify a inline function. But we can just quote humps. And then a is 0, b is 2. Okay, so we can execute that, and we get an estimate of 29.3262. That's the analytical estimate, or the numerical estimate of the integral. And we don't know if this makes sense or not, yeah? Now, we can analytically derive the result. If you write out that function, you can derive analytically the derivative, and the result is identical. Here, that's a function hump int, and that's especially written here. This is the result if you analytically integrate this function, you see a lot of terms. Okay, so you don't need to know this, but this is just to benchmark whether our result makes sense. Obviously, we could have also done this with the Lobato quadrature, and we can then compare the difference between the two, and you see, so instead of using quad, we now use quad L. Again, the same bounds, 0, 2, same function, just a different function, different integration rule, and you see that the difference that I get between Simpson and Lobato is marginal. Nou ja, I can also use trapezoidal integration rule, and you see that this is the result I'm getting, which is, nou ja, if this is the analytical result, is that you're a little bit off. And for this we need to use 21 x values, okay? So I specified here on top, I don't know if you've seen that, I specified that x had a step size of 0.1. So between 0 and 2 with a step size of 0.1. So these quad functions are really easy to execute, yeah? Because you don't need to specify which x values you use, you just specify the lower and the upper bound, okay? So here I just execute the trapezoidal rule where I specify x values, and humps x will give the corresponding f values, the function values. Now we could have also done this with Gaussian quadrature. Yeah, so imagine that we had two nodes, and we know that with two nodes that the first node is minus 1 over the square root of 3, the second node is 1 over the square root of 3, and that the corresponding weights are 1 and 1. So then we are between 0 and 2 because our function is between 0 and 2 instead of minus 1 and 1. So we need to, once we have the x values, we need to scale them linearly from minus 1 to 1 to the domain 0 to 2. And that's what we do with this rule, yeah? So now we have the c values which are now between 0 and 2, whereas x was between minus 1 and 1. Just a linear transformation. We calculate the function value at those z values that are between 0 and 2. And now what we can do is we calculate with Gaussian quadrature with two nodes, we get 34.2786, whereas we know that the analytical result is 29. So we're pretty far off, but that's because we only use two x values. Okay? So obviously we can use more than two x values with Gaussian quadrature. We can use 5, 10, 20, 30, 40, 50, 100, 200, and what you'll see. So each time I loop over each value of n, size n, 2 means that's just the number of elements in this horizontal vector. So for each value of n, I determine the optimal location of x and the associated weights. And the optimal location of x is between minus 1 and 1. So the next rule is where I scale those values between minus 1 and 1 to the range of 0 and 2, where a is 0 and b is 2. So I linearly transform the optimum x values, which are between minus 1 and 1, according to Gaussian quadrature, to the domain of interest. Then I evaluate the function, and then I just fill out the integration rule, which is b minus a divided by 2 times the sum, the product or the sum of the product of the weights and the corresponding function values. Okay, so if we do this, then now what I'm going to get is a list with Gaussian quadrature, and what you see here is you see that if you use more x values, I can I, G, Q, oh, and then nx, and I think it's, yeah. So here you see number of x values versus the estimate of the integral, analytical, the numerical estimate, yeah. So we can plot in one figure then, if you like, the difference between what we get with Gaussian quadrature these are the number of nodes we use, the number of x values, and on the y value is the distance to the actual analytical value of the integral between 0 and 2. So what you see is that you need about 30 nodes, 30 here, that you're getting in the right ballpark. And with 40 you're actually pretty good. Okay? Now, so I show that there's another function here. Very quickly, what I want to talk about is improper integrals. So far, we've always worked with integrals in which I tell you what a and b is. I tell you that a is 0 and b is 10. So the lower bound is 0, upper bound is 10. Or any other value. What's now an improper integral is one in which the lower bound is minus infinity and the upper bound is infinity. So how do you use that in a computer program? Yeah? Like if I have a normal distribution statistically, then I know that the integral between minus infinity and infinity of that normal distribution is equal to 1. But how do I insert minus infinity and infinity in my computer program? So here's an example of a part of a normal distribution where I specify my inline function is exponent minus x squared. And now I just integrate between 0 and infinity. So a is 0, b is infinity. You see, the code is not doing it. It gives an error. So it actually says that the integral is not a number. So in other words, you cannot use infinity as b. So now what we can try then is let's try a really large number, 1e to the power 100. So that's 1 with 100 zeros. So still, it doesn't take it. So let's try something else then. Let's try another really large number, 1 with 10 zeros. Now it suddenly takes it and gives us an estimate. And that is what is called improper integrals. And what you see for the experts here is that this is close to the analytical result. Because it's a normal distribution. So we know, what you remember, that it's 1 over the square root of 2 times pi. So, and we do that to scale the integral to 1. And in any way we get the same result. The analytical result is the square root of pi over 2. So if I use 1e to the power 10, I'm going to get an integral that's very close to the analytical integral. So this is what's called improper integrals, where a or b or both of them are like infinity and you don't know what to do with it. Okay, so that's it for this chapter. I quickly want to move on now to the final project, okay? So let's open some document here. Because probably some people might be confused, like how is this working? And teaching 2013, final assignment, oh no, that's, where are we? Oh, this is C20, am I right? Interesting. Okay, here we are. Okay. Now, so the question is, you see this map here, okay? Yeah? We all see this map. This map was created from interpolation. Okay? You see 1 through 10. So in other words, imagine that you do some survey of the soil or so, yeah, for construction. You need to know what type of soil do we have in this area, so that you know what type of construction you would need for your building. And imagine that you only do 10 measurements, okay? So at 10 different x and y locations, you determine the soil type, and that you end up with 10 different soil types. So you have X and Y, and you have that 10 times. Once you have those X and Y values, you determine that my first XY value is soil type 1, then 2, all the way through 10. So what you have then is you have 10 different combinations of X and Y with a corresponding soil type. Then you use that information, because then you only have point information. Then you have 10 points on this map. 10 points. And you're like, I like to make a nice map to show it to someone. Then you go to MATLAB and you use a function that uses those 10 original locations to do a nearest neighbor interpolation from which it derives this map. Now the question is, can you tell me from this map where the location of the original 10 measurements were? Now, and let me show you how that works in practice so that you're not confused. So let's clear everything, okay? So let's first specify that I have some, I just show you how to make a map like this, okay? So then you can maybe, you get some ideas. So the first thing I do, I know that my map had 100, was 100 by 100 cells. It was also in the document. You see, I have 100 cells here, and I have 100 cells in the Y direction. So I have 100 by 100, so I have 10,000 cells. So each cell is either a 1, a 2, a 3, a 4, a 5, a 6, a 7, 8, 9, or 10. But let me just give you an example, give you more insight. Here what I do, I randomly create 10 X values and 10 Y values that range between 1 and 100. Okay, so what I have now is X. So these are my X and Y values, okay? Now what I do is I want to interpolate on a 100 by 100 grid. So I use this option mesh grid, and we have discussed this in class, okay? So I say I have X values between 1 through 100, and I have Y values from 1 to 100. And if I don't specify the step size, you know the step size is 1. So X is going to be 1, 2, 3, 4, 5, etc. And Y is going to be the same. So this gives me Xi and Yi. So this is how Xi looks, and this is how Yi looks. Okay? So they're matrices of 100, size Xi, size Yi. They're 100 by 100. Now what I do is I use this option grid data, which I allude to in the PDF, where I say, you know what, I have my original X and Y locations. The first row of X and Y is soil type 1, the second row is soil type 2, the last row is soil type 10. And I want to interpolate that to Xi and Yi, and for that I want to use nearest neighbor interpolation. So now MATLAB gives us an estimate, and let's see what happens now. It's not supposed to give an error. If I use a p-color here, you see, this is the map that I get from that. This is the map that I get from this. So based on the randomly created X and Y points, and I interpolate those X and Y points to a map that's 100 by 100, this is the result I get when I use nearest neighbor interpolation. So the question now is, can you, based on the map that I gave you and the text file, so you know for each grid cell 1, 1, 1, 2, 1, 3, 1, 4, you know for each grid cell, you know the corresponding value of the soil type, 1, 2, 3, 4. You have that. So you have a file of 100 by 100 filled with numbers from 1 through 10. And now the question is, can you, based on that information, retrieve the original location where the measurements were made of x and y. I now just randomly created some x and y values. The question that I pose to you is, can you tell me, because the x and y values that I use for this map are these values. So the first is 3354, 2511, 0.1789, etc. Okay? Obviously, if I create different, if I do this again, yeah, now I have different estimates of x and y. Or I do this again, I get different values, and now I interpolate this, I do the same story over again, but now with different values of x and y of the location. So a measurement location is first column, second column, x and y combined. Yeah? So the first measurement is 84.35, that was the x value, the y value was 96, etc. So we have 10 measurements, and then the soil types are 1 through 10. So this one had soil type 10, this one had soil type 9, this one had soil type 8. So let's now interpolate this thing. And what you see is we get, let's see here, we should be getting, P color. This is now the result. You see, so I get a different map than what I just had previously, because my measurement data points changed. So each measurement has an x and a y location. So if I'm in this room, I have an x coordinate and I have a y coordinate. So I ask you, can you tell me what the original 10 locations were of x and y? So what you see, that if you change it randomly, that you get a different map. Now my question is, tell me those 20 values. So for x and y are both 10 values. So essentially we have 20 values. Tell me those 20 values, 10 for x, 10 for y, that created the map that is in the PDF and that I sent to you in a text file. Yeah, I like to know, I want to have this one back. Yeah? So in Lee's case, you need to use grid data. So somehow you need to have a computer algorithm. You cannot solve this analytically. Somehow you need a computer algorithm that tells you what x and y should be, or that starts from some initial value of x and y. And I suggest that you start at the geometric mean of each individual soil type. Okay? Because 1 is likely going to be somewhere in this area. It's going to be 40, 50. It's going to be a good initial guess for 1. 2, a good guess might be 30, 85. Yeah, 30 here, 85 here. So start with a well-educated initial guess. Then create the map with grid data. Subtract the original map that you had in the ASCII. Calculate the absolute difference and the sum of squared error, like least squares. Okay? And then propose a change to x and y. And then accept that if that new xy configuration creates a new map with a lower error than the original x and y you started with, you accept that new x and y. So this is what it's called an optimization problem. But you cannot solve this with F0, because F0 can only give you one variable, can only deal with one variable, x. We now have 20 variables, because we have 10 x values and 10 corresponding y values. Why is this important? And I try to allude to this. Because in the scientific world and community, people are hesitant to share data. They share these maps, okay, and they then think, oh, that based on this map, we cannot derive the original measurement location. But you can. You can do that. So the group that is closest, I have the true results here. if you go in my directory, oh, not here. If you see here, actual locations, that's a .mat file, and that has the actual locations that I used with grid data to create the map that you see in the PDF. For each group, follow carefully the instructions, and next week I will say something, maybe on Monday, about the algorithm you can use to improve the x and the y values. I hope it's now clear what the goal of the exercise is. The question now is, how do I make better estimates of x and y? There's algorithms, computer algorithms for that, that are quite simple that you can implement. So you do this iteratively. You create a new cache, you create the map associated with that cache, you calculate the error, and then you check, is it lower or not? If it's not lower, you reject that new cache and you stay at your current cache. And that's how you keep going. And ultimately what you should see, that your positions are getting better and better, and that the map that you are creating is getting closer and closer to the map of the PDF that you have in the text file. Okay? Next week, the Monday group, most people, I believe, everyone except one student has signed up for another session. So everything has been arranged, but please carefully read, because some people have to, we might be in a situation that some students have to take their own computer with them because there's not enough computers. Okay, but anyway, things have been arranged, and next week a little bit more information again about the final project. Start early, okay?